All right, here's another cool biasing circuit. We've got emitter biasing circuit analysis coming at you. So here's our emitter bias circuit. And one thing I want to point out is whenever you see a point or a power point like this, we've got VCC and VEE, we've got two supplies here. Whenever you see a single point like that and it looks like it's not connected, the other side of that power supply is connected to reference. It's implied. And so our VCC up here, for example, we've got the plus side tied to the RC, the collector resistor. Now the negative side of that VCC it's implied that that's tied to the reference. Just like at the bottom we've got our minus VEE tied to the emitter resistor. Well, the plus side of that VEE is tied to reference. So here we have the schematic on the right, and we've actually physically drawn in the implied connections of the schematic on the left. And this schematic makes it a lot easier to see the Kirchhoff loop equations. So if we start our loop equation in the bottom left of the schematic, we go up through VEE, we get a minus VEE, we've got a plus VRB, plus VBE, and plus VRE. And that is our Kirchhoff loop equation. We just write it right around that bottom loop right there, and we can now derive the base current. So once we've got the base current, then we can quickly calculate the collector current and the emitter current. We can find the voltages on those two resistors. And we want to now do another loop equation all the way around through VCE so that we can find the VCE voltage. And this bias configuration is a little bit different than some of the previous ones because we've got two power supplies in there. And so in order to find VCE, we're going to Kirchhoff all the way around the outside of this loop. And we're going to start the same spot as we did before, start at the minus VEE, but we're going to go straight up through the VCC. So we get a minus VEE minus a VCC plus a VRC plus our VCE plus our VRE. And all that should be equal to 0 according to Kirchhoff. And now we can solve for the VCE of the transistor. All right, so now we need to work on our load line, our DC load line. And we're going to treat the circuit as though the transistor is an open switch, and that's going to be our VCE cutoff. So if the transistor was an open switch, there'd be no current flow in the collector or the emitter. And so if we write the Kirchhoff loop around there, same as before to find VCE, we would see that if this transistor is acting like an open switch, we should see VEE plus or VCC plus VEE, the total voltage for VCE cutoff. And then saturation is the same thing or very similar. Now the transistor is acting like a short, and so we have that full potential across the collector resistor and the emitter resistor, and so our IC saturation would be VCC plus VEE divided by RC plus RE. So that's a little bit different because we've got two supplies in the circuit. And then our Q point is the same as before. It's our VCE and IC point. And hopefully again, like I mentioned in the previous videos, we need our Q point. If we're going to be an amplifier, we need our Q point to be somewhere in the middle of the active region, which is between IC sat and VCE cutoff, preferably close to the middle.